All right. Well, thank you, everyone. And it's really my great pleasure to have the opportunity to talk about histotripsy and histosonics. So what is histotripsy? The term, when we actually coined histotripsy in 2002, because all medical terms is based in Greek. So histo means soft tissue, and the trypsy means mechanical breakdown in Greek. So the intention is that it's the first non-invasive technology to perform the real surgery, meaning that do it in a mechanical way. So imagine that you have ultrasound delivered from outside the body. See, this is the ultrasound device here. And it's focused in the target tissue with a millimeter accuracy. So what you're seeing here is you are seeing a cluster, a cloud of microbubbles generated. And it's about the size of 2 millimeter by 4 millimeter also. And it's 14 centimeters away from the ultrasound transducer. And that bubbles kill the target tumor without incision, without radiation, without injury. And that's what I'm about to show you. So what are the clinical benefits of histotripsy? Why do we need to do it? First, non-invasive. As I mentioned, that the ultrasound is actually delivered from outside the body. And what you are seeing here is an actual patient case. There's a tumor actually deep in the liver. If this patient is treated with conventional surgery, what you will see is a lot of injury to the liver here. But this patient was treated with histotripsy. And histotripsy liquefied that tumor to acellular debris. And that acellular debris is absorbed over time by the body. And you can see 30 days later, that tumor is actually not tumor anymore. It's just liquefied debris here. And it's substantially reduced already. And most importantly, there's no damage to the surrounding or overlying liver at all. Second, high precision. So what we are doing here is we rely on using ultrasound to generate microbubbles, which is termed acoustic cavitation. And that is a threshold phenomenon. So bubbles are only generated when the focal ultrasound pressure is above a threshold. You can see actually the histology slide of tissue treated by histotripsy. And typically what you see is you have intact cells like this. In the histotripsy treated region, the cells mechanically disrupted entirely. Okay? So those are debris, then the body just cleaned it up. But what you will see here is you can see at the boundary, there is a half of the cell, and the half of the cell cut off. It's because our effective scalpel here are microbubbles on the size order of a cell, and incredibly precise. If you have pressure above the threshold, you have damage within the treatment region. And if it's below the threshold, then you have no damage at all. Therefore, we don't see the same partially damaged region like radiation you will have seen, or thermoablation then caused by actually heat perfusion. So it's a highly precise procedure. Third is real-time image guidance. For a non-invasive procedure, one thing is that the clinician is not seeing everything with their eyes directly because they're not opening the patient up. However, with histotripsy, what we are doing is we have an ultrasound image. And what you are seeing here is from a patient treatment, and the red circle here is the tumor outlined by the clinician that he's trying to target. And then the red cross here indicates the ultrasound focus. And see the bright spot here behind the red cross? And that is a bubble cloud, a cloud of bubbles generated by histotripsy. And the bubbles are natural contrast agent for ultrasound. Therefore, you can see the bubbles generated in real time. And that help the clinician to guide and monitor the treatment, even without opening the patient up, to maintain the high safety and the treatment accuracy. Next, most of the patients that they wake up from histotrypsy procedure, by the way, it's a one-session treatment. The patient come in, and the clinicians put them down and just scan and remove the tumor, and that within, depending on the size of the tumor, within a couple of hours, they wake up, and our record right now is actually 10 tumors in one session treated. But typically, patients wake up, the first thing they ask is, have you done anything to me? Because they don't feel the pain. There's no pain. They immediately should go home and have dinner at home and being able to return to normal activity the second day. So we're talking about a form of cancer care, not like chemo or radiation therapy has significant side effects. It's non-invasive and also increase the quality of life. You are getting a tumor treatment with dignity and allow you to still live a normal life. Next, tissue selective. So what we found out is that the critical structures in our body, such as normal blood vessels, and this is actually, by the way, is a histology showing liver tissue treated by histotrypsy. So you can see the critical structures like normal large blood vessels and nerves and the bile ducts. They actually remain intact in the histotrypsy treated region when the surrounding liver tissue or tumor tissue get completely destroyed. It's because those critical structures, they naturally have a high mechanical strength and more resistant to the mechanical damage. And this allows us to actually go in, and we have seen in treating high-risk locations. We have seen clinicians treating a tumor sandwiched between vessels that is surgically inoperable. And the clinician was able to go in, destroy that tumor, and the vessels remain entirely intact. Lastly was a surprising finding from our research, which is this immune stimulation. And I will talk about the mechanism more later. So it turns out that histotrypsy also stimulates this potent immune response, and such that in selected patients, what we have seen that is treating one tumor can lead to substantial regression of other off-target tumors. And this is in a patient where this patient really coming very late stage, liver look like Swiss cheese with so many tumors in there, and the treated tumor is not even on this image slice. But what you see here is, look at all those tumors. And 8 weeks later, substantially regressed due to the immune stimulation effect induced by histotrypsy. So I'm going to talk about 25 years journey to bring histotrypsy from a concept and to the first time I observed the phenomenon as a PhD student, and eventually this whole map. So 2001, I started my PhD, and 2002, first observed the phenomenon. And 2004, I published the first paper on histotrypsy, and we coined the term histotrypsy at University of Michigan, and I was in that publication. And spent the almost 10 years to really trying to design and build a specialized equipment for histotrypsy and understand the mechanism behind it. And December 2009, co-founded Histosonics with a goal to really bring this to the patients. And 2016 was the first clinical trial, actually, and it was performed in prostate, so benign prostatic hyperplasia. So that was the first human trial, and unfortunately, the results from that clinical trial was mixed and didn't meet the goal. And years later, we found out it's because the human patients and our preclinical animal model, they don't actually match well. We switched to liver, and 2017 built the first liver human system, and 2019 had the first human trial in cancer and also in the liver. That was in Spain, and the results were fabulous. And that led to 2021, the multi-center trial we call Hope for Liver trial. And guess what? COVID. So the trial was really hard to do, as you can imagine, from recruit patients, the whole thing. But however, the results, again, super positive. And that led to the FDA approval in 2023. And it's for non-invasive histotripsy treatment of liver tumors. And 2024, we started a clinical trial for Hope for Kidney, so for treatment of renal tumors, because it's a platform technology. So it really can be used to treat any solid target. Again, going really well, enrollment complete, and hopefully the data will be submitted to FDA soon. And we started in December 2024, the pancreatic cancer trial, and it's ongoing, and the results look really good so far. And I was told the number, I showed 25 patients treated, but the new number is, I think, 3,000, actually over 3,000 now. So we have treated over 3,000 patients in the United States, in Europe, UAE, and Asia, around the world, and now hopefully in Australia soon. And 2025, really recently, had this recent acquisition, now evaluated the company at $3 billion. So 25 years in one slide. And I was trying to break down to the key critical moment early on before you can actually see the demo. So 2001, why actually at that moment that inspired me to look into invent histotripsy? So I remember I was a new PhD student at University of Michigan, and there is this pediatric cardiologist. His name is Ahi Ludomirsky. So he came in and he asked one question. So he was operating on pediatric patients, very sick patients with congenital heart disease. They are very little kids and babies, and they were dying on his operation table because they were so sick that they couldn't endure the invasive surgery. So he came in, he asked our research group at biomedical engineering department, he said, can you invent a non-invasive interventional technology that can perform the real surgery? And he emphasized on the real surgery. And why? Because there was already, there's radiation, right? And there's a different kind of form of thermal ablation using different energy to generate heat to kill the tissue. But they leave the tissue in situ. Even you kill the tissue, you're not removing them, not like a real surgery. And he needed something to do the real surgery for his patients with congenital heart disease. So he asked, can you actually invent a non-invasive way to perform the real surgery to allow me to save those really sick kids? And I was in the audience, and I thought, this is such a wonderfully impossible idea that it's a perfect PhD dissertation for me. So I went to Ahi and went to my advisor and said that I would love to take this as my PhD dissertation. And my mentor looked at me for a second, and he said, well, if you do this, my advice is do not read any papers for the initial time, because I do not want your innovative mind to be restricted by conventional thinking, which he means that the current literature says it's impossible. Okay, but I started it. So my first year of PhD life involves I go to slaughterhouse every week to do dumpster diving of pig hearts. Now I bring to the lab. Literally, when I say dumpster diving, I'm not even kidding, because I literally go in and they just give me a black trash bag. And then they showed me where a big trash can is, full of pig organs. And then they charged me $5, but I can fill the trash bag with whatever organ I want. So that's what and no gloves, right? You go in and you get it. So anyway, so I did that for for the first year. I go in, I get pig heart, and I come back and I dissect them, put them in the water tank. So what you'll see here is a piece of pig heart tissue in my holder, and I have ultrasound transducer that placed actually 10 centimeter away, and I trying to target. And then I was using all kinds of parameters and trying to test. And as expected for the first year, it was failures after failures and after failures until this day. And this is the experiment that I did, and you are here to actually see what I saw in 2002, more than 20 years ago, that first experiment. So what you're going to see here is that I want you to actually look at this spot. And this is in a water tank, by the way, okay? So you will see a video here. And the video here is I run over to turn on the amplifier. And you will start seeing almost like a smoke coming out. But remember, it's not smoke because it's a water tank. You can't get smoke at all. And this is all in real time. So you see kind of smoke coming out. Then you start seeing a minute later a beautiful perforation through the peak atrial wall tissue. So what happens here is that was the first time I witnessed that using ultrasound with microseconds length pulses at really high pressure that allow me to actually break up tissue to submicron size ACL debris. That's why it looked like smoke. And again, like I said, a minute later, I see a perforation. Sound is not touching here, okay? So I can tell you that I did it first time, and I thought I was dreaming. Because after a year of failure, I was like, this is probably just me trying to, wish this will happen. So I did it second time. And I still couldn't convince myself this is real. And my rule of thumb is if you can repeat the same thing 3 times, it must be real. So I did it 3 times, and I remember I need to turn on the camera. And did it 3 times. And again, it happened again. And I ran over to Charles King, my PhD mentor's office. I said, Charles, you need to come over here because something very special just happened. So that was the first time I actually saw histotripsy. However, after that, within about a month or so, and I want to actually, before that, I should show that this is the equipment I actually used back then to generate the first histotripsy experiment. You can see this is a transducer from 2002, and that was a single element 788 kilohertz transducer, and it's run by this amplifier. So it's one element, and run by this amplifier. This amplifier was the most powerful amplifier in the world at that moment, and it's ENR E1000 amplifier that gave you 1,000 watts of the power to drive the transducer, and it has to be run by a 380 volts electrical power, right? We really have only one plug in the entire university that can enable this amplifier to run, and the cable is 4 feet long, and I claim that space. Like, nobody touch it. This is my space. I'm going to cover this with Picard. You don't want to touch it anyway. So that was, 2002. But however, a month after my first successful experiment, I had to run over to Charles' office again. And I said, Charles, I have good news and bad news. The good news is I was able to repeat the experiment. So this is real. The bad news is that I just broke the most expensive equipment in our entire lab. But I don't think it's my fault. I think because we don't actually have a histotripsy work back then, I said to make this work, even the most powerful equipment, commercial equipment at the time, is not sufficient. If we are serious about this, we have to design and build our own specialized equipment. Should we do it? And Charles, as crazy as I was, said yes. And it was funny because we knew that we couldn't do it with a commercial equipment. So when we published a paper in 2004, the first paper, the entire scientific community, after reading that peer-reviewed paper, had one response, and the same response that they kept telling me for 10 years, which is, it's impossible. Histotripsy is impossible for two reasons. One is you would not be able to generate the histotripsy parameters in a robust way, even with the best commercial device. And second is we don't know how it works. Mechanism is entirely unknown, and cavitation, which is microbulb activity, was a phenomenon have known at the time to be entirely random. For 50 years, nobody can control it, so you can control it either. So that was the thing, the kind of community response. So first, we spent 10 years almost to trying to design and build the specialized device. So I just want to fast forward 20 years later. Don't know why it's blurry, but 20 years later, this is a more recent device we built. So this is a single element transducer. Here is a 260 element histotripsy ultrasound array. So 260 elements, which we build by 3D printing. And this is an amplifier. Remember I said this is an amplifier that's as tall as me, right? And drive one single element. This is an amplifier, has 8 channels. It can fit on my palm. Each one has 4 times power than this. And not only it can generate histotripsy, it can also receive signal to do imaging as well, to help us with monitoring and doing some really fancy stuff. And if you actually, and so now people don't think it's impossible anymore with this device, but it took us almost 10 years to even get started and 20 years to really get to this form. Second, about the mechanism. And if one thing is unknown for a scientist, it's opportunity. So what we did is I set out and we went and we got ultra high-speed camera and a microscope, and we started studying bubbles, how bubbles work. So what you are seeing here is the two critical things of the mechanism. The first thing is how bubbles, microbubbles, can be generated in a controllable and predictable fashion with ultrasound. So what happens is that we are breathing air, so we have nanometer gas pockets in our tissue because it's filtered by the lung. So it's wonderfully stable. The surface tension is actually 200 times of the atmosphere, really high. But however, imagine if you have a gas pocket, like a balloon almost, and you can make the pressure outside the balloon lower than the inside, which means physics-wise overcome the surface tension of that gas pocket. You can make it actually expand, and eventually it will collapse. Which means that if we can, within microseconds, generate over 200 times of the atmosphere, but negative pressure, because remember, I need to go the pressure outside than the inside of the balloon, so negative pressure. Then we can actually expand the gas pockets and later collapse. So what we happen to see here is Charles King, my PhD advisor, Adam, Eli, my former PhD students, we were a team. Now they're professors too. But we spent almost, I would say, 15 years in doing some crazy experiments together. So what do we show here is that, if you're actually looking at tissue, most tissue are water-based. So Adam and Eli actually went to the same slaughterhouse, get every single pig parts they can get, from liver to pancreas to kidney, and also build actually blood and blood clots and everything. And then what they found is that we found that if you have a one cycle of ultrasound pulse, and if your negative pressure is in the window of 26 to 28 megapascal, which is more than 200 times of the atmosphere, then we can reliably expand nanometer gas pockets to 100 micron within a few microseconds. That is 100,000 times of expansion, then followed by collapse. So we're talking about a bomb, but microscale, okay? And then we see the video here. So this video is taken under microscope using an ultra-fast camera, so the activity you're about to see happens within 100 microseconds, and then slow down tremendously for you to be able to visualize. So what we're seeing here, those white structures here, are breast cancer cells embedded in a clear tissue mimicking gel. And the black structures here are microbubbles generated, but they coalesce into one big one. So what you see here is that when the bubble expands, you can't really see the cells in the middle, but at the periphery, you can see when the bubble expands, cells get squeezed. When the bubble collapses, cells really get pulled apart. And if you have enough force, you really pull cells, bisect cells, as I showed you in the histology earlier. So really, it's this bubble cell interaction generating high local mechanical strain and stress that pulls cells apart. And in a very local way, if you are out here where no bubbles and you do not see that kind of cell damage. So now we solved the two major issues, equipment and the mechanism. And I want to talk about the wonderful discovery later, which is historytrypsin stimulates the immune response, which is what I did not anticipate at the beginning. And it was a wonderful discovery along with Dr. Cliff Cho, who is a cancer immunologist. So what we found is that historytrypsin is a very unique interventional technology. Unlike radiation, use ionization, or ablation like radiofrequency ablation or microwave ablation, which are the form of ablation technology using heating, right? Different energy, even using laser or ultrasound. So both ionization and heating, they kill the tissue by denaturing the protein. Therefore, you kill the tumor antigen. With historytrypsin, we disrupt the cell membrane, allow the tumor antigen to come out, but they are still functional. So then we do the first thing, which is release the tumor antigen to the body, which is critically important. Why? Because the cancer, they do two things really well. One is that the body immune system should kill any foreign things that are attacking our body. But however, the cancer, they actually help turn off the signal pathway so that the body cannot just kill them right away. And that checkpoint inhibitor therapy that won the Nobel Prize is supposed to tackle that problem. Then the second thing is the cancer hides really well. So the body can't even detect them. Therefore, a lot of cancer do not get diagnosed until really late. Here, when we disrupt the cell membrane, they can no longer hide. The tumor antigen come out, and the body see them and said attack and tag, right? So that's the first thing to trigger the immune response. And second is historytrypsin treatment causes immunological cell death, which is something that we can spend hours on. But things like necroptosis, apoptosis, and ferroptosis, that's another thing in the immune cycle. And third is inflammation, which is actually part of the immune response too. So a cascade of those events together allow the historytrypsin to stimulate the immune response. And in this figure showing in comparison to radiation therapy or radiofrequency thermal ablation, historytrypsin induce so much more CD8 plus T cells. To the degree that we actually perform the experiments that with a mouse, implant 2 tumors and treat to only 1 tumor, but we monitor both tumors. And being able to see that historytrypsin actually stimulates CD8 plus T cells in both the treated side and also the contralateral untreated side as well. And interesting enough, this only happens if both tumors are of the same tumor line. If you have 2 different tumor types, right? Imagine you have one side a liver tumor, the other pancreatic tumor, then you wouldn't see the same response at the contralateral untreated side. But if they are of the same tumor line, to the degree that this is the experiment, we actually use a melanoma just because it's a tumor that is dark, so you can see the color. So this is a mouse where had pulmonary metastasis, means that have metastasis over the lung. We only treat a primary tumor with historytrypsin only, nothing else, and then you are able to see that the metastasis reduced significantly due to the immune response generated by historytrypsin. And we were also so surprised to see that this actually also seen selected patients as well. And now there's this research ongoing and hopefully lead to clinical trials soon is to combine historytrypsin with immunotherapy to enhance their effects. There are things we still need to adjust on the historytrypsin parameter side to really maximize the immune response, but this will elevate the treatment from just a non-invasive local ablation to a systemic cancer treatment. And that would further increase the impact. And another exciting thing about this is that we found that histotripsy can stimulate immune response, right? We showed not just local, but systemic. And also not just in what people characterize as hot tumors that responsive to immunotherapy. It actually stimulates immune response in cold tumors that's immune resistant to immunotherapy. So that will really expand and increase the patient population that can really benefit from actually getting cancer treatment utilizing our own immune system. So all that research is able to actually result in this FDA-approved Edison system that you will see later. And you will see the patient video and the demo. So I will end this with having a professor moment for a second. I like to think about that modern medicine, the revolution of the modern medicine is really all kind of generated, all really fundamentally pushed by innovation, technology innovation. 1860, when anesthesia was invented, that's the first time the surgery was made possible. And that made a huge impact on medicine, and that's the start moment of the modern medicine. 1900, Madame Curie discovered radiation, and that enabled radiation therapy in 1910, where you start seeing that patient can actually get treatment from radiation, even though it's toxic, but it can actually treat tumor without, doing the surgery. 1960, really big revolution, technology innovation from optics, where the endoscopic and the laparoscopic surgery become possible because you can go in with a small lens, allow you to actually see target inside, so you don't have to perform surgery by opening really the whole thing. You can do small incisions and go in to do laparoscopic surgery or endoscopic surgery. So every 60 years, there's a big technology innovation that now really change how medicine is practiced. It's another 60 years. The time is right now that the medicine whole movement is moving towards minimally invasive, non-invasive. And it's my belief that the next era of medicine is entirely non-invasive surgery. And it's starting from histotripsy. And not just liver tumors, renal tumors, and pancreatic tumors. We're looking at different targets also from breast tumors, prostate tumors, thyroid tumors, anything you think of. Now we can actually treat through the skull, even into the brain, not just the tumors and also neurological disease and the stroke. So there are so many things histotripsy can do, but today you will see a clinical Edison system here to start with actual clinical patients with liver tumors and see how it's in action. Thank you.